Okay, we're going to look at the second part of the fundamental theorem of calculus. So we're going to define our capital F for these examples as the integral of a lowercase f, and those f's will be given below here. So we're going to do it several times for different functions and see what happens. We're going to find out what f of x is equal to, and then we're going to take its derivative and find out what the derivative is equal to. All right, so we're going to start with number one. So capital F of x, I'm just kind of using this up here, is defined as the integral from 1 to x of the function of lowercase f, which is 4t minus t squared dt. We'll come back to this, but notice that the x is not the same variable as the variable in the integrand, the t and the dt. Okay, we'll get back to what's happening there. We may talk about it in class as well. But those, when you define a function as an integral, using an integral, those variables have to be different. So that's our f of x. So if we compute the integral using the fundamental theorem of calculus, first I have to integrate this thing. So it's going to be power rule, 2t squared minus t to the third, and then 1/3. Okay, and then we're going to integrate that, or we're going to evaluate it from 1 to x. So then capital F of x is equal to 2x squared minus 1/3 x cubed. Remember, sorry, this was f of x minus capital F of 1, right? So we're doing the fundamental theorem there. I'm going to kind of take that away. So that's the f of b part. That's the f of the upper minus f of the lower. So it's going to be 2 times 1 squared minus 1/3 times 1 cubed. So when we simplify that, capital F of x is going to be equal to, that's 2x squared minus 1/3 x cubed. And then we've got minus 2 plus 1/3. So if we write that in a better order, capital F of x is going to be equal to negative 1/3 x cubed plus 2x squared minus 5/3. If I take the derivative, which is what they want, so by the way, that's our f of x. It was defined as an integral. I could actually integrate and just turn it into the function that it is. So just to kind of show you, those two things represent the same thing. I can write it, I can leave it in integral form, or I can write it out as the function. In this case, it's a polynomial. That should be a third there, sorry, a cubed. And now they want what's f prime of x. So now if I take the derivative of this, I get negative x squared plus 4x. So essentially what's happened here by the final answer, f prime, f was defined as an integral. So if I integrate a function and then take its derivative, we're looking for a pattern here of what's going to happen. There might be a faster way to do it. Let's look at the next one. So capital F of x is defined as, again, this integral here. So the integral from 1 to x of cosine of t dt. So I'm going to actually integrate now. I want to do this out and see what function I get. So the integral of cosine is sine of t. And I want to evaluate from 1 to x. So that means I'm going to plug in the upper bound first. So I get sine of x minus sine of 1. So that is our f of x. This is the function. These two functions are the same. One's an integral form, and the other one we've just written as a different type of form, like it doesn't have the integral in it. We've already integrated. And now we want to take the derivative of that. So the derivative of sine is cosine of x. The derivative of sine of 1 is 0, because this is just a number, sine of 1. There's no variable in it. Just like pi is a number, or e squared is a number. So our derivative here is cosine of x. And again, what we're trying to do here is look for a pattern. If we integrate a function and then take its derivative, what ends up happening? Okay, now we're changing up our definition of f of x. We're going to define f of x now as the integral from 1 to x squared of these functions. And we're going to do the same thing. So I'm going to write capital F of x as the integral from 1 to x squared of t cubed dt. So then when I actually integrate here, I'm going to get 1/4 t to the 4th, and I want to do that from 1 to x squared. So when I plug in the x squared, I get 1/4 x squared to the 4th minus, when I plug in the 1, 1/4 1 to the 4th. So my capital F of x in this case is 1/4 x to the 8th, because I multiply those exponents when I have a power raised to a power, minus 1/4. So there's our F of x not written in integral notation or integral form. And then if we take the derivative of it, so again, I've taken a function, I've integrated, and now I've taken the derivative. And so when I take the derivative, I get 2x to the 7th. We're looking for that pattern. What happens if we take a function, we integrate it, and then we take its derivative? All right, let's look at this one. Again, f of x is defined as the integral from 1 to x squared of 6 times t to the 1/2 dt. So when I integrate, I go for power rule. I'm going to get 2/3 times 6. That's going to be 4 t to the 3/2. And I'm going to evaluate from 1 to x squared. So that means I plug in my x squared for t, and then minus when I plug in my 1 for t. So my capital F of x, remember I'm multiplying my exponents in this situation, so 2 times 3/2 is just 3, so that's going to be 4x to the 3rd. This is just 1. 1 to the 3/2 is 1, so 4x to the 3rd minus 4. And then if I take the derivative of that, I'm going to get 12x squared. Again, we're looking for a connection here maybe between the derivative and the original function. That's what we're going to be talking about. Can we get there a faster way without having to do this integration and then derivative? Because we know at this point that derivatives and integrals are inverse operations. They should undo each other. It sort of looks like it here. If I take my derivative and go back to the function that I integrated, they should be the same function. It's working here. It's not working down here for this integral. So the question becomes like, what's going on with that integral? So first we're going to take a second and we're going to write a definition for the second fundamental theorem of calculus. It's really just kind of part 2 or whatever. So we're going to say if capital F of x is equal to the integral from a, where a is a constant, to some function of x here. We did x on the first one, and then we did x squared after that. Of a different function, f of t, then the derivative of that function is going to be f of g of x times g prime of x. All right, so the connection, we'll see what this means a little bit after these couple examples, but the connection here is that we're going to see that derivatives and integrals undo each other. So what was going on here in this case? Well, if our function is defined from 1 to x squared, this is really our variable in this function. And so our inner function, if you think of chain rule, the inner function is x squared. So we have to apply chain rule here. Okay, so if we look at these original ones here, the inner functions are just x. So the question really becomes, to get to the derivative, right? If I take the integral and then I take the derivative, I'm back to the original function. So what ends up happening here is that we can just take that x and plug it in for t in both spots, and that is what we get for our answer, for our derivative. And you can see that chain rule does not apply here. Because I mean, we're using it, but x is just, the derivative of x is just 1, so I don't have to worry about multiplying by the derivative of the inner. In this case, you can see that these functions don't look exactly the same, but what I'm going to say is that I take the x squared and I plug it in. If we apply that rule, right? And I get, let me do this in a different color. We're looking for a shortcut. We know that if we integrate and then differentiate, we should just get back to the original function. So all we really need to do is plug x squared into that function. And I get x to the 6th. That function is not quite the answer yet. That's because we have to apply chain rule. So when you do this idea of plugging the upper limit in, that's where we're doing the derivative of the outer. You can think of it that way with chain rule. That's the derivative of the outer while recopying the inner. Because when you do the derivative of an integral, it's just itself, and I'm recopying the inner, so I'm just kind of putting the inner function inside. But then it needs to be times the derivative of the inner. So the inner function's x squared, so it's times 2x. So if I do x to the 6th times 2x, I get 2x to the 7th. Now it matches. Okay, we're going to look on this page here and do some the faster way. All right, so this is the connection we're making. So what's the derivative from the last page that we did? The derivative on the first one, I'm going to write it in a better format. I'm going to write it as 4x minus x squared. And then this one was going to be cosine of x. Right, that's what that one was. Then 2x to the 7th. And this one was 12x squared. All right, so now they want us to apply the second fundamental theorem of calculus. So it looks like what they're saying here is that all I have to do is plug the upper bound, g of x, right, because that was this guy here. I just have to plug that into f. There's no derivative here. Notice there's no primes on these. If I just plug the upper bound into the function, that's the derivative of the outer while recopying the inner, then times the derivative of the inner function. We have to apply chain rule. All right, so let's try this here. If I plug x in, I get the derivative of this integral turns out to be 4x minus x squared. Okay, and then we would do that whole thing times the derivative of the inner function, which was x. So the times 1 doesn't do anything for us. So that's the faster way to do it. If you're trying to find the derivative of an integral, we know that we just have to plug the upper bound in to our variable. What about the lower bound? Why does that not matter, by the way? If we look here, whenever we plug in the lower bound, all it always results in is some constant in f, right? It just keeps resulting in a constant. Over here it was this guy. We combine the two constants. And what happens when you take the derivative of a constant? It goes to 0. So we don't have to worry. This can be any number we want. It could be 1, it could be 7. As long as it's a constant, we don't worry about it in this one. We're taking the derivative. We integrate, it does something, but then when we take the derivative, if it ends up being a constant, it's just going to be 0 anyway. All right, so let's look at this one. If I plug x in, I get the derivative is equal to the cosine of x. That's the derivative of the outer, recopying the inner. And again, I know I'm saying derivative, but it's because I integrated, then took the derivative, so nothing changes. Times the derivative of the inner, which is just 1. Okay? All right, let's look at the next one. So the derivative is going to be, I take the upper function and I plug it into our function in the integrand here. So I'm going to get x squared to the 3rd. And then times the derivative of the inner function, which is x squared. So the derivative of that is 2x. So the derivative is going to be x to the 6th times 2x. And when I simplify that, I get 2x to the 7th. All right, and this is one of our main uses of the second part of the fundamental theorem of calculus. We're looking at an integral as a function, and taking the derivative of that function is pretty easy. Okay, so there's going to be some questions where a function will be defined as an integral, and they're going to ask you about the derivative of it. We've already seen some in some of our practice FRQs, even though we didn't officially talk about it. When we talked about the park, people entering and leaving the park, when we integrated that, it ended up just being the functions themselves, right? When we took the derivative of the integral of that. So it's a similar idea to that last part of that problem. But now we're kind of officially learning it. And the key here is that these variables do not match. They have to be different. This variable has to match that variable. That's the function. That's where you're plugging in your x. So if I ask you to find like f of 2, we're plugging 2 into the top there. We are not plugging 2 into the t. So that's important to notice. And again, we're going to talk about why. It's probably easier to do it in class so we can have a discussion where you can ask questions back and forth. But notice that these variables match because that's the function. These are not the same variable that's in this function. Those have to match each other but be different. They're just sort of the function for the integral. Oops, I'm going to erase that. All right, last one here. So if I take my x squared and I plug it into the function, I start taking my derivative. That gives me the derivative of the outer while recopying the inner. So I'm going to raise it to the 1/2 power. And I'm going to say I'm putting in x squared. The inner function was x squared, so I go times 2x because that's the derivative of the inner. If I simplify, x squared to the 1/2 should be x to the first. So that's 6x times 2x, so that should be 12x squared. That's our derivative. And if you notice, for all of these derivatives, they match the way when we did it the long way. So that's how you're going to take the derivative of an integral. We're going to use this shortcut here. We're going to apply chain rule. Don't forget this part. Okay? So let's do some examples here. Find the derivative of each of the following functions. So notice these functions are defined as integrals. So when I take the derivative of an integral, I just need to plug this in for t. So I'm going to get the square root of 2 minus 2x squared, and then it's going to be times 2. The times 2 is the derivative of 2x. It's the derivative of the inner. So f prime of x is going to be equal to 2 times the square root of 2 minus 4x squared is how we'll leave it. All right. So what do we do with this guy when we have the limits are, the function is not on top? It's got to be in that form where the function goes on top. So we're going to have to apply our property of limits. So if I negate this integral, then I can call it negative 3 to x squared. And now I can take the derivative. So notice I didn't do any derivative here on this step. It's going to be negative e to the cosine of x squared, and then times 2x, because that's the chain rule part right there. So I usually write it with the 2x in front. All right, let's look at another one. So h prime of x, I'm going to take cosine of x and plug it in for t. So I'm going to get cosine of x squared, and then times the derivative of cosine is negative sine of x. Don't forget to use your parentheses here so it doesn't look like minus sine of x, but it looks like times a negative. All right, so then I can rewrite this a little more simply as negative, we'll go cosine squared of x sine of x. Okay, then there's, I mean, you can stop here. You could go a little further. We know that what cosine squared is really going to be 1 minus sine squared of x times sine of x. Then I can distribute the sine of x, and I'll distribute this negative with it as well. Like if I brought the sine in front, I'd really be distributing a negative sign to both of these, right? So I'd get negative sine of x plus sine cubed of x. You could also simplify to that. I'm okay with either one of these. It's just the multiple choice thing, right? If this is a multiple choice question, you kind of have to see some of that simplification. So keep in mind, again, I've said it before, and I still think this is the way to go. Like when you start to see trig function squareds, that's when you can change them into 1 and minus 1, like all those things. I'm looking for 1s in sines and cosine squareds. Those are your Pythagorean identities. That's how you can watch out for those. All right? But as far as for me on a test, if you wrote this out or a quiz or a homework, I'm okay with either answer. Okay, now let's see if we don't have functions, right? This is how we do it when we have the functions and stuff. What if we have a graph? They love these graph questions, okay? So This is a graph of g, which is in the integrand. Okay, so when we integrate g, we're talking about the area underneath g. F, though, is defined as this entire function. So find the value of f of 0. So f of 0 means it's the integral from -4 to 2 times 0 of g of t dt. All right, so what we're really doing is we're integrating. So in this case, since we have a graph of g of t and not the equation, we've got to use the graph. We're going to integrate from -4 to 0. So it's all this area here. All right, now I can see that the height here is 1 and the height here is -1. So this area here is going to cancel out the positive and the negative. So we just need to find this area over here. I'm going to say that I'm going to do a rectangle, a 2 by 1 rectangle. So that's going to be 2 plus the area of this quarter circle, because it's got a radius of 2 in both directions, right? The radius is 2. So I'm doing a quarter of pi r squared. And that's going to come out to be 2 plus pi. All right, so that's the value of f of 0. F of 0 equals 2 plus pi. Find the value of f of 2. So now that's the integral from -4 to 2 times 2 of g of t dt. So that's going to be equal to from -4 to 4 g of t dt. You can pause the video here and try to work this out on your own. We're going and see if you get the right answer. We're going from -4 to 4. So pause the video, see if you get the same answer that I do. All right, welcome back. So you should have gotten 4 plus 2 pi. If you didn't get that, you can ask me in class about it. Find the value of f prime of 1. So now we've got our f of x, but we want to find the derivative of that. Then we plug in the 1 afterwards. We're not plugging in the 1 straight away. Let me recopy f down here so it's a little easier to see. So we've got f of x is defined as the integral from -4 to 2x of g of t dt. So if we want to find f prime of that, because we want to do the derivative first and then plug 1 into it, that means I'm going to plug 2x in to the function here. So I'm going to get g of 2x, and that's going to be times 2. That's our definition of f prime. So now if I want to find f prime of 1, that means I can do g of 2 times 1 times 2. So that means I'm looking for g of 2 times 2. And g of 2 on the graph here, if I go to 2, g of 2 is 1. So I've got 1 times 2. The answer is 2. So don't plug in the 1 first into the top of the integral. You've got to take the derivative, leaving this as an x here. Do your derivative work, and then plug it in afterwards. You take a second and try to find the value of f prime of -2. And then see if you get the same answer as me. So you can pause it and try it. All right, welcome back. I got -2. So again, you can ask me in class if you're having trouble with that one. What if we have to do the second derivative of 2? So let's start with this. We know from above that f prime of x was g of 2x times 2, right? Now we're going to do the second derivative. This looks like a chain rule right here, right? This is a constant. Maybe I'll write this like 2 times g. I won't even show the times. We'll write it as 2 times g of 2x. So the constant 2 comes along for the ride. We do the derivative of g of 2x is going to be g prime of 2x. And then it's chain rule because there's an inner function of 2x, so then times 2. So f double prime turns out to be it's 4 because I have that 2 here. So I'm going to multiply these 2's. Get 4 times g prime of 2x. So now I want to do f double prime of 2. So I've got 4 times g prime of 2 times 2. So this is going to be equal to 4 times g prime of 4. So how do I find g prime of 4 on this graph if this is a graph of g? If I go to 4, g prime of 4. So if I look at 4, I want the derivative there at 4. So we're going to be looking for the slope of the tangent line there. And since it's the endpoint there of the interval, that function is not differentiable there. We don't know what happens on the other side of that, right? So this would just be, it's undefined. So f double prime of 2 is undefined because it's not differentiable. G is not differentiable there, so we can't figure out, this is causing the problem. We can't figure out that number because it's undefined there. If I had to ask for f double prime, say, of 1, when I plug the 1 into all this, right, this would have been a g prime of 2. So I would have been at 2, still undefined, so that's a bad example. If I did 1.5, if I said f double prime of 1.5, we would be at 3, and on 3, I know what the derivative is there because it's a nice straight line, so we could have figured out the derivative and got an answer. All right, let's move on. Here's another one. So I'm going to have you pause the video and do number 1 and number 2 from using the graph and the information here and see if you got it right. Okay, welcome back. So for this one, you would have gotten 1. And this one, we would have gotten -8 plus pi. So we can talk about it in class again if you didn't get those. Remember this one, you're integrating backwards now, so you got to think about that, about what happens with your positives and negatives. All right, let's look at finding the derivative of g. So if g of x is defined as the integral from -1 to x of f of t dt, that means g prime of x will be defined as, I plug x in, so it'll be f of x, and then times the chain rule, the derivative of the inner function x is just 1. So g prime of x is just f of x, so g prime of 6 will be equal to f of 6. So f of 6 from this graph here, this is the graph of f of x, or I should say f of t. What value were we looking for? At 6, f of 6, if we go up to 6, we're at 2 on the y-axis, so f of 6 is 2. All right, now let's find g prime of 2, so I want you to take a second, pause the video, and do that. Okay, welcome back. So you should have gotten -2. Let's look at doing the second derivative now. So g prime of x, we know from above, was f of x. We already did that part, right? So now g double prime of x is equal to f prime of x, and the inner function's x, so it's just 1 again. So g double prime of x is equal to f prime of x. So now we want to find g double prime of 2 would be equal to f prime of 2. So since we have a graph of f, let's go see what the slope of the tangent line is at 2. At 2, x value of 2, again, we have a cusp here, looks undefined, right? So we're going to say, and it says give a reason, so we're going to say that g prime of 2 is undefined. Because f prime of 2 is undefined, because f of x has a cusp at x equals 2. All right, let's try g double prime of 4. So we know that g double prime from the previous one of x is f prime of x, so g double prime of 4, -4, should equal f prime of -4. So we're looking for the derivative at 4, at an x value of 4. So f prime of -4, sorry, not 4. So we're looking for the slope of the tangent line there. So since it's on a line, the slope of the tangent line is the same everywhere. So we need to do this slope formula. It looks like we go down 2 and over 1. So it looks like our slope is -2 on that line, all the way down the line. So we're going to say it's -2. Whoops, got ahead of myself. Give a reason for your answer. You could say f prime of 4 of negative, I keep saying 4, of -4 represents the slope of the tangent line drawn to f of t at x equals -4. So actually in front of that I should have said g prime double prime of -4. And I don't need to say that part. We know that it's f prime of -4. So we'll just leave it like that. All right, let's move on. So here's another one where we have a graph of f. And hold on a second here. Okay, so yeah, we've got our graph of f. Here's one where they define g using the integral of f, but they also throw in another function that's not an integral, so they're kind of giving us two parts. Luckily, there's addition there, so I can kind of take the derivative of them independently of each other when I need to. So they're just trying to mix us up by throwing one function in there like regular function, and then one where our function is defined as an integral. All right, so first they want us to just see if we can find g of 3. So that's going to be equal to 1/2. We're just plugging in 3 everywhere for x. And remember, it doesn't mean that you plug 3 in here. That's not the variable of the function g. This is the variable of function g. All right, so now, since we have a graph of f of t, we got to use the graph to evaluate that integral. If we had the equation, we would integrate and use the equation. So from 0 to 3, so we're integrating from right to left. We're going to assume that that's right at 1.5. All right, so it looks like our bases of our triangles are equal. Are our heights equal? That goes up to 3 and down to 3, right? So yeah, those are equal areas, one above, one below. So the integral from 0 to 3 is just going to equal 0. So our answer here is 9/2. All right, find the value of g of -4. So you're going to pause the video here and see if you can do that on your own. Okay, welcome back. You should have got 8 minus 2 pi. And now we're going to do some derivative work. So g prime of x. Well, first we should write what g of x is. It'll be easy to reference if I write it again. G of x is equal to 1/2 x squared plus the integral from 0 to x of f of t dt. So then our derivative is going to be x. I just did power rule on this first part. Plus, now I plug the x in. X plus f of x times the derivative of the inner function here, which is 1. Just want to mention it. All right, so g prime of x is defined as that. So g prime of 3 is going to be equal to 3 plus f of 3. So if I look at the graph, f of 3 is -3. So we've got g prime of 3 equals 3 plus -3. So g prime of 3 equals 0. Now let's do the second derivative. So we already have from before the first derivative is equal to x plus f of x. So the second derivative should be equal to the derivative of x is 1 plus f prime of x times 1 because the inner function is x. I'm not going to show that part. So now we want to find what's g double prime of 2. That's going to be equal to 1 plus f prime of 2. So we got to go to the function f, look at the slope of the tangent line at 2. So we're on this line segment here, so whatever the slope of that line segment is. So it looks like we go down 1, 2, 3, 4, 5, 6, and right 3. So it looks like it's -6 over 3. So it's going to be -2. Looks like to be the slope. So that slope is -2. So I'm going to get g double prime of 2 equals 1 plus -2. So g double prime of 2 equals -1. Oops. All right.